If you can hear me. So, yeah, I think it's not working. Full screen. Yeah. Okay. Thanks for the introduction and thank you for giving me the opportunity to speak over here. So today I'll be talking on some of the work that we have been doing recently in frictional granular matter. So it's universal laws in frictional granular matter is very rare. And so we found some of the scaling laws when a frictional granular matter, compressed granular matter is approaching unjamming transition. And so this is a work with Itamar Procaccia and George Henschel. So before moving on to the main thing, let's try to take a quick overview of what really is a granular matter. Now, as you can see from the picture that granular matter is present everywhere, starting from sand dunes to coffee beans. And they are basically collection of macroscopic objects. And at this length scale, the thermal fluctuations are negligible, and that means that the system is far from equilibrium, and the states are purely controlled by the external driving. The system will remain in the same state if you do not drive the system externally. And at the contact length scale, the interaction is purely repulsive, and you have also the friction into the system, which makes things even more complicated, because with the friction you have force indeterminacy, which brings history dependence into the system, because then you need to mention that how you have prepared the system. And this granular matter has some peculiar properties, in the sense that, So this has some peculiar properties. Sometimes it behaves like a solid, and sometimes it can flow, depending on some conditions. So what are the conditions that really govern this transition from solid to liquid, and how they are different or similar to the thermal disordered media? So in order to get a quick overview of the transition that takes place across different disordered media, a jamming phase diagram was proposed long ago by Liu Nagel, where you have three control parameter: temperature, 1/, density, and load. Now, for a supercooled liquid, if you reduce the temperature below the glass transition temperature, then you will form a glass. And for colloidal suspension and granular matter, if you increase the packing fraction substantially, then you will reach a point where the system will be able to resist the external deformation. Then that means the system is jammed. So we are basically will be focusing on this load density parameter space. So why we are doing this? Because if we are able to understand the failure in frictional granular matter, then I think we can extend these ideas to the more complex phenomena that occurs in the nature, like in forms of landslides and avalanches, snow avalanches. So So this is a typical force chain network in the simulation of granular matter, where I have compressed the system uniaxially. And you can see that clearly there is some inhomogeneity in the way the stress gets transmitted from one point to another. There are some brighter spots, which means the force chains are carrying much of the load, where the darker spots are not carrying that much of the load. So, so the stress transmission is non-trivial, and so if you reduce the pressure of this system, then how the force chain network reorganize, or how the failure takes place. So we would like to understand those things. So in order to do that, we took help of the numerical simulation. So this is the interaction potential that we had considered. We had considered both the Hookean and the Hertzian case. So this is pretty standard. And so this is the elastic part, and this is some viscoelastic damping. And you have also the tangential part. And as you have friction in the system, then that tangential force is constrained by the friction coefficient times the normal force. So this is a typical initial configuration in our simulation box, where bidispersed particles have been put randomly into the system, and then we kind of uniaxially compress the system until it reaches jamming point, and also we go above the jamming point. And then again, we cyclically decrease the pressure to go back to the zero pressure point. So this is the typical pressure versus packing fraction curve that we get out of the simulation. Here you can see that clearly the decompression curve is not following the same path along which the system was compressed. So there is some finite hysteresis. So mainly we are interested in this decompression leg, like how the slips or how the system fails as it approaches the jamming point, unjamming point. So the quantity that we are interested in measuring is the number of frictional slips that takes place if you reduce the pressure from P plus dP to some P. So we calculate this PDF, and we can also calculate the cumulative distribution from that PDF. And from the simulation, we did the measurement, and as you can see that as you go to low and as you go to lower pressure, as the pressure tends to zero, the frictional number of frictional slips kind of tends to diverge. Okay, so why does this diverge, and if it even diverges, how does it diverge? Like, is there any exponent or amplitude to which, is there some scaling equation that we can form from some simple scaling theory that will tell us that in the thermodynamic limit there is some divergence? So in order to understand this scaling theory, I would like to remind you of some of the scaling laws that are already existing in the jamming literature. So in case of frictional granular media, this jamming point, as the pressure tends to zero, is dependent on the friction coefficient and also the preparation protocol. But for a given preparation protocol, it only depends on the friction. As you can see on the right, that there are larger voids in the system, but the system is still jammed and stable because it has stability being imparted due to the higher friction coefficient. Long ago, Matthew proposed that there is a rigidity length scale that diverges as you approach the unjamming point. And also it has been seen in the simulation that you can see from this that there are two systems where this system is very far away from the jamming, and this system is very close to the jamming point. And you apply a point force and kind of observe that how that kind of gives rise to the fluctuation, and to what extent that fluctuation propagate. And you can see that close to the jamming, you have a kind of length scale that diverges. So, yeah, so that length scale seems to be diverging with an exponent nu from the critical jamming point. And also you have a power law scaling of pressure if you are above this critical point. But this exponent, the exponent with which this length scale diverges if you are above this jamming point, is independent of the dimension of the system and also independent of the interaction potential. But this exponent with which the pressure diverges is dependent on the interaction potential. And for the Hertzian case, for the nonlinear interaction, you will have an exponent of 1.5, and for the Hookean case, the exponent is 1. So you can combine this, and you can see that with the pressure, as the pressure tends to 0, that this length scale kind of diverges with an exponent nu by psi. So we say that this same rigidity length scale also controls the number of frictional slips at a given pressure, because the thing is that within that length scale, the system behaves as isostatically. That means the number of constant is equal to the number of degrees of freedom. And that kind of makes the system marginal, and you'll have all sorts of unstable floppy modes. So we say that below that length scale, there are local sleep avalanches everywhere in the granular matter. And as you can see from the picture, that if this force chain network reorganizes, if you kind of decompress the system, then most likely places where the slips will take place are along these force chains. And clearly you can see the dimension of the force chain is obeying this. So it's between 1 and Euclidean dimension, which is 2 for our case. And it seems that for the uniaxial compression protocol, the linear force chains dominate, and we took the dimension of the backbone of the force chain to be 1. So sleep events are considered to be avalanche of length scale xi, which is pressure dependent. And within that length scale, and from the consideration of the dimension of the backbone, then you can calculate what are the number of grains that are associated with that force chain, and that number of grains will be scaled like epsilon by the particle diameter to the power some exponent ds, which is the dimension of the backbone. And with the system size also, these regions increase like this L by xi to the power d, which d is the Euclidean dimension. And so then there are this many regions, each of which is containing this many sleeping disks. So from simple scaling analysis, you can find out like what is the number of frictional slips that take place, what is the number of frictional slips takes place at a given pressure. So from doing that scaling analysis, we found that this is the kind of scaling that we get out of those scaling analysis, and we'll plug that into the expression for the cumulative PDF, and we'll integrate from P to P max. And so if we do that, then you can see that clearly you can express the cumulative number of slips in terms of some exponent and also some amplitude. The amplitude is given by something like this, and the exponent is a combined product of all the other exponent. And there is a parameter called C, which is dependent in the simulation number of decompression steps that you take while going from P max to P. So in order to test our theoretical prediction, we also calculated the same parameter in the simulation, and this is what we found. Like from the theory that the exponent is 1, as it has been shown earlier by various people, that this exponent with which the length scale diverges close to the jamming point is of the order of 1, and also the for the pressure power loss exponent is 1.5, and the backbone dimension is 1. Then we'll get an exponent of 0.66 for the Hertzian case with a friction coefficient of 0.1. And from the numerical data, we also fitted it, and we got an exponent of 0.64. And we also used the same n that we used in the simulation, and we kind of got an amplitude which is very close to the theoretical prediction. So in order to also increase the trust in our theory, we also changed the interaction potential, and we did it for the Hookean case, and this is what we had found. Like for the Hookean case, only this exponent changes to 1, and then the exponent is going to be just 1. And from the simulation, we also found an exponent which is closer to this 1. And so it seems to be matching quite remarkably. And we also did it for many different friction, and you can see that for different friction also things to be in good agreement with the theoretical prediction. So why does this diverge? Like we also kind of calculated this distribution, like the tangential force minus the friction coefficient times the normal force. So this will tell you that number of particles that are close to the Coulomb threshold. And as you can see, if you go to very low pressure, you'll find that a lot of contacts are residing at the Coulomb threshold, and it kind of says that the system is kind of marginal state. And if you slightly part of the system, then we'll see lot of floppy modes and instability. So this is intimately linked to the plastic contacts, and also for the frictional media, it has been proposed that if you take this sliding contacts into the consideration, there is a picture of the generalized isostaticity that also kind of gives similar scaling compared to the frictional case. So this is my summary, so we have decompressed the compressed granular media, and the fragile configuration is generated at low pressure, and we observe giant frictional slips as the fragile state collapses as we approach the unjamming transition. And this instability is understood in terms of a scaling theory. And we had theoretically predicted amplitude and exponent, and amplitude seems to be diverging in the thermodynamic limit. And in the future, we'll study different deformation protocol to see like whether this also holds for different cases or not. Thank you. Yes, yes.
So in the subsequent analysis you did, what do you use as the jamming? Did you have to sort of assume a jamming density? And how do you?
Yeah, so the thing is that, so as you were talking about the cyclical oscillatory training of the system, so we also train the system. So for the frictional case, it can jam at any point, like depending on so if you cyclically train the system, then it will progressively, the jamming point will get shifted to higher and higher packing fraction. Okay, but sometimes, so after a lot of cycling, you will find that the system loops into the same configuration. It doesn't change that much. So we study that configuration where these states are not important. Like.
Is it also dependent on how far you increase the density?
Yeah, that is also true. Like, so if you so the thing is that if you want some history independent measurement, then you need to be in a kind of steady state where there is no hysteresis in the system.
What could be the role of polydispersity on your framework? Because polydispersity is known to change the nature of the chain forces and so on.
Yeah, polydispersity will play a role, but the thing is that scaling closer to that jamming transition seems to be also valid for the polydispersed case. Okay, so that is kind of universal. So that is not going to change the overall picture of that we had drawn from our simulation.
At some point in your theory, you identify psi, which is the length associated with rigidity.
Yes.
So the size of the slip events. Is this an assumption, or is this something you derive?
No, so this is a kind of assumption because we didn't check in the simulation. That's what we are doing in the future work. Like we are going to directly check what is this length scale. Like, but from the Matthew-Watt derivation of the rigidity length scale, it says that below that length scale, the system is isostatic. Okay, so that means that cannot be explained by normal elasticity theory. So that is just close to fall. Like, so we kind of say that that is the landscape that also governs the plastic strip events in the frictional media, and that seems to be giving a quite remarkable match with the simulation.